Chemistry, we're beginning our second unit now, and it's on chemical reactions, and this is putting together chemical compounds and atoms and molecules to make other chemical compounds. That's really what chemistry is all about. We're going to start with a concept called molar mass. So a mole. A mole is that number of anything. Could be a mole of cars, a mole of giraffes, it doesn't matter. It's just a number like a dozen donuts, a dozen eggs. A dozen means 12. A mole means that number. Now this number is called Avogadro's number, but in daily usage we say mole. In scientific notation, a mole is written 6.022 times 10 to the 23rd. So now it's one of the reasons we use scientific notation to deal with really big numbers like that. Remember, we can think of an atomic mass unit as the mass of a single proton or a single neutron. So here's the problem. We can't measure the mass of a single proton, neutron, atom, or molecule on a scale because they're too small and they're too light. So what do we do? Well, an oxygen atom has a mass of 16 atomic mass units. So you know that oxygen, if you look at your periodic table, has 16 protons and 16 protons and neutrons. It has 8 protons and 8 neutrons. And each proton and each neutron has a mass of 1 atomic mass unit. So if you add up the 8 and 8, that's 16 atomic mass units for an oxygen atom. But we can't measure 16 atomic mass units on any kind of scale. We measure mass in grams. That's the scales that we have in the classroom are measured in, are calibrated in grams. So we have scales for that. So look over there on the right. What if we knew how many oxygen atoms it would take to have a mass of 16 grams? Instead of 16 atomic mass units, it would be the same number, 16, but it would be calibrated or measured in grams, something that we can actually measure on a scale in the real world. Then by knowing the number of grams of oxygen we had, we would know how many oxygen atoms. In other words, if we took oxygen and we put it on a scale and it weighed 16 grams, then we would know exactly how many atoms we have because we figured out how many atoms does it take to get from 16 atomic mass units to 16 grams. But how many atoms? What is that number that gets us from the mass of one oxygen atom, 16 atomic mass units, to the exact same number, 16 of grams? How many atoms would that take? Well, the answer is Avogadro's number, 6.022 times 10 to the 23rd. This is the number of atoms that will convert the mass of a single oxygen atom at 16 atomic mass units to the same number of grams, 16 grams. So there goes our question mark, and here comes our answer. So if you can take one oxygen atom at 16 atomic mass units, and now you multiply that by 6.022 times 10 to the 23rd, so you have that many oxygen atoms, then the mass will be 16 grams, something that we can actually measure on a scale. So again, the significance is if we weigh oxygen and we see that we have 16 grams, we'll know exactly how many oxygen atoms we have. 6.022 times 10 to the 23rd, a number that's so big we couldn't possibly count it. But we can know it by knowing how many grams of oxygen we have. How Avogadro figured out that number is something that's for discussion later in the course. It's not important at this point. Just understand that he figured out that that was the number, and it's been used ever since. So this is the atomic mass. It's the mass of one atom, 16 AMU. And this is called the molar mass. It's the mass of 1 mole of oxygen atoms, and that's 16 grams. So when you look at your periodic table at oxygen and down beneath the O on oxygen, you see the number 16.00. You can either think of that as the mass of a single oxygen atom, but that's not very helpful because we can't weigh AMU. We have no scales for that. We want to start thinking of that 16.00 as the molar mass of 1 mole of oxygen atoms, and that's going to be 16 grams. So this relationship is true for any element or compound by taking the atomic mass in AMU, that's what you find on your periodic table, and multiplying by Avogadro's number, 6.022 times 10 to the 23rd. So carbon, if you look on your periodic table, it has a mass of 12.01. If you multiply that by Avogadro's number, then you get the molar mass, which is also 12.01, but it's in grams, something that we can actually weigh on a scale. Nitrogen, look at your periodic table, it's 14.01 AMU, but if you take a mole of nitrogen atoms, it will be 14.01 grams. Neon, look at the periodic table, it's 20.18 atomic mass units for a single neon atom, but if you take a mole of neon atoms, that number, then you get 20.18 grams. Aluminum, 26.98 atomic mass units, a mole of aluminum atoms, 26.98 grams. Sulfur, 32.07 atomic mass units, a mole, 32.07 grams. Here are some common examples of chemical molecules and compounds. So H2. So what does H2 mean? What does that little 2 mean? It means you've taken 2 atoms, 2 hydrogen atoms, and you've bonded them together to form 1 hydrogen molecule. And that forms a molecule. If you remember back a couple of lessons, that hydrogen is one of the 7 elemental diatomic molecules. It means in nature, you don't find hydrogen atoms floating around in the atmosphere. You find them as H2 molecules. Anytime you have a hydrogen atom, it's going to look around for another hydrogen atom, and it's going to bond with it and form an H2 molecule. H2O. It's 1 oxygen atom and 2 hydrogen atoms bonded together. That forms a molecule. Those are covalent bonds because that's a non-metal. Those are 2 nonmetals. H and O are nonmetals, so they form a covalent bond. They share electrons. CO2, same thing. 2 nonmetals. They share electrons. That's made of 1 carbon atom and 2 oxygen atoms. Now in H2O, you notice there's no subscript beneath the O. That means it implies that there's a 1 there. If you don't see a subscript, it doesn't mean 0. Then there wouldn't be an oxygen there at all. It means 1. Carbon dioxide, you don't see any subscript below the C. That means there's 1 carbon atom and then 2 oxygen atoms. NaCl, that's 1 sodium and 1 chlorine, or really sodium and chloride ion. And that's not a molecule, that's an ionic bond. Sodium is a metal, chlorine is a non-metal, so they form an ionic bond. So that's not technically called a molecule, but I'll tell you, we'll loosely refer to NaCl as being a molecule, or we'll call it the molecular formula, but it's really a unit cell. So if you keep repeating NaCl, NaCl, NaCl many, many billions of times, you'll end up with a salt crystal. O2. So that's 2 oxygen atoms, just like the H2 up above. Oxygen is a diatomic molecule, so whenever there's a lone oxygen atom, it's going to find another oxygen atom and bond with it to form an O2 molecule, and that's a molecule. So that's the oxygen that you breathe in every time you take a breath is not an oxygen atom, it's an O2 molecule. Let's go down these, by the way, in terms of compounds, just as an aside here. H2 is a molecule, but it is not a compound because it's not made up of 2 or more elements. H2O is a molecule, and it is also a compound because it's made up of 2 different elements. CO2 is a molecule, and it's also a compound because it's made of 2 different elements. NaCl is technically not a molecule, it's a formula unit in a crystal lattice structure of ionic bonds, but it is a compound because it's made of 2 different elements. And finally, O2 is a molecule, it's covalently bonded, but it is not a compound because it only has 1 element. The small number after atoms is called a subscript. So those little numbers up there are subscripts. A subscript of 1 is not written, as we just mentioned. H2 and O2 are covalent bonds that form molecules. They are not compounds because they have only one element. If a number appears in front of a chemical formula, it means that there are more than one molecule or formula unit of that formula. So 2H2O means there are 2 H2O water molecules. So in those, if you have 2 H2O, that means you have a total of 4 hydrogen, you can see them there in the diagram, and 2 oxygen atoms. So what does that 2 out in front of the 2 H2O do? It basically multiplies through to everything inside that formula. So you have 2 H2. So 2 times 2 is 4, so that means you have 4 hydrogen atoms. And then 2 times the 1 O in the formula means you have 2 oxygens, and there you see 2 oxygen atoms in the formula. So it's kind of like distributing a number through parentheses when you multiply through parentheses in math. It's kind of the same concept here. So 3 CO2. So here we see 3 CO2 carbon dioxide molecules. So if you look at that, you have 3 carbons and 6 oxygens in 3 CO2 molecules. So the 3 out in front, you multiply 3 times 1 carbon is 3 carbons, and you multiply 3 times 2 oxygens in each molecule, that equals 6 total oxygen atoms, and you can see in the diagram that that's the case. You have 3 carbon atoms and 6 oxygen atoms. So that's the way the coefficient applies to every element in that particular molecule, not just the one in front. 4O2 means 4 oxygen molecules. So if you look at the diagram, 4 times 2 would equal 8. So there are 8 oxygen atoms in 4 molecules. The large number in front is called a coefficient. It indicates how many complete units or how many complete molecules that you have. The atomic mass of a molecule or unit cell is computed by adding the atomic masses of each atom times the number of atoms. In moles, this is the same number, but it's measured in grams. So the atomic mass of a single water molecule looks like this. It has 2 hydrogens. Each hydrogen has an atomic mass of 1.01. Remember, that's the average mass of all different isotopes of hydrogen. So on average, each hydrogen atom has a mass of 1.01. So you add that, and then you have a second hydrogen. You add that in again, 1.01, and then oxygen has an atomic mass of 16. You get those numbers off the periodic table. So for a water molecule, 2 hydrogens and 1 oxygen, the atomic mass is 18.02 atomic mass units. So for a single atom or molecule, we're dealing in atomic mass units. So those are all from the periodic table. Now the molar mass of 1 mole of water molecules, that is, you multiply it by 6.022 times 10 to the 23rd molecules, everything's going to look the same. The numbers are exactly the same. The difference is, however, the units of measure for 1 mole is grams. So we've converted the same numbers, 1.01, 16, 18.02, to those same numbers down below, except now they're measured in grams. And that's a useful unit of measure for us in the real world because we have scales that measure things in grams. So that's the mass of 1 mole of water is 18.02 grams. So again, what that means is if I take water and put it on the scale and I weigh it and it weighs 18 grams, 18.02 grams, that means I know I have exactly 1 mole, 6.022 times 10 to the 23rd molecules of water. That's an amazing fact. There's no way we could ever count 6.022 times 10 to the 23rd of anything, molecules or anything else. But if we know we have 18.02 grams of water, so we have to know two things. Exactly what it weighs in grams and what is the substance. It has to be pure water. It can't be mixed with anything else. As long as we know we have pure water and that we have 18.02 grams, it means we know we have exactly 6.022 times 10 to the 23rd water molecules in our container. So let's just do another example. So now we're going to use methane, CH4. Remember what the technical name for methane, CH4 would be? It would be carbon tetrahydride, but no one ever calls it that, ever. It's called methane. It's also known as natural gas. That's what natural gas is. Okay, so let's say we have 2 moles of methane. So we can think of that 2 out in front as either molecules of methane or moles. But we're going to think of it as moles now. So it's the same numbers from the periodic table, except instead of thinking of atomic mass units, we're going to think of them as grams, as long as we're dealing with a mole, 6.022 times 10 to the 23rd, and not a single molecules. So over there on the right, you see you have 2 carbons, so that's 2 times 12.01. You get those numbers off the periodic table under carbon. And you have 2 times 4 is 8 hydrogens. So that's 8 times 1.01, and you can see all those added together down there. You add all that up, you get 32.10. And if we're talking about moles, that is multiples of 6.022 times 10 to the 23rd molecules, then 2 times 6.022 times 10 to the 23rd is going to equal 32.10 grams. So these numbers are the atomic mass numbers from the periodic table, but we're now going to think of them as molar mass. We're going to think of those as grams there, and that's the mass of an entire mole, 6.022 times 10 to the 23rd. All right, now we're going to work some problems where we can kind of play around with these numbers and see how many grams, how many moles, whatever it is we're trying to figure out. So I'm going to have you fill out some of these tables. So here's a table for water, H2O. So over on the left column, we're going to fill in the element. So water has hydrogen, it has oxygen, and when you put those together, you get H2O. That's the compound, that's the molecule. The next column is how many of those do you have in a single water molecule or a mole of water, well, single water molecule. You have 2 hydrogen, you have 1 oxygen, and that's a total of 1 water molecule. Don't make the mistake of adding the 2 and the 1 to get 3. Think of it like this. To make a bicycle, you need 2 wheels and 1 seat to make 1 bicycle, not 3 bicycles. So 2 wheels, 1 seat is 1 bicycle. So 2 hydrogens, 1 oxygen is 1 water molecule. You put those together to make 1 water molecule. So now the atomic mass is going to be, for hydrogen you have 2 of them, and each one is 1.01 from the periodic table, so that's 2.02 atomic mass units. For oxygen, you have 1 oxygen, and from the periodic table, it has a mass of 16 atomic mass units. So now to get the total mass of a water molecule, you do add those numbers together, and that will give you 18.02 atomic mass units. Okay, now we're going over to the important columns. This is moles, because from now on in this class, we're going to try to think of everything in terms of moles. That's big units, big baskets of molecules, 6.022 times 10 to the 23rd, that are big enough for us to actually see with our eyes and weigh on a scale. So we decided that a mole is going to be 6.022 times 10 to the 23rd. So we're going to multiply everything by that. So 2 atoms of hydrogen becomes 2 moles of hydrogen. 1 atom of oxygen becomes 1 mole of oxygen if we multiply by that number, Avogadro's number. And finally, 1 mole of water, 1 molecule of water becomes 1 mole of water right there. Now we could have defined a mole as any number we wanted and said, well, if you multiply that number and we defined it as a mole, let's say 1 times 10 to the 20th, we'd still have 2 moles, 1 mole, and 1 mole. That's not the significance. The next column is the significance. It's that the 2.02 atomic mass units turns into the exact same number, 2.02, but in grams. There's only one number in the whole world that will make that conversion exactly go from 2.02 to 2.02 grams, and that's 6.022 times 10 to the 23rd. No other multiplication of atoms or molecules will make that conversion happen, that numeric conversion. And that's the significance of Avogadro's number. So we have 16 atomic mass units for a single oxygen atom. That becomes 16 grams if we have 6.022 times 10 to the 23rd of them. And finally, the 18.02 atomic mass units for water becomes 18.02 grams if you have a mole, 6.022 times 10 to the 23rd. Now, there are times we're going to want to know the number of atoms and molecules. And this is, again, the amazing thing is you can actually count or know the number of this uncountable number of atoms and molecules called a mole by knowing exactly how many grams you have and what exactly the substance is. So it says we have 2 moles of hydrogen, so that's going to be 2 times 6.022 times 10 to the 23rd, and that's going to be 1.204 times 10 to the 24th atoms. So in 1 mole of water, you're going to have 1.204 times 10 to the 24th atoms of hydrogen. Amazing. You can know that incredibly large number by just weighing. For oxygen, you have 1 mole of oxygen in a mole of water. So that's simply going to be 1 times 6.022 times 10 to the 23rd. So there it is right there. And the same for the water molecules. It's going to be 1 times 6.022 times 10 to the 23rd molecules. All right, so I'm going to have you fill out some of these and answer some questions. So let's answer a few questions. Now let's look at that red box first. You have a large red box, and then you have a small red box. Everything in the large red box relates to what's in that small red box. To make 1 mole of water, you need all of those things you see in that red box, all of those relationships. So let's just go through them. To make 1 mole of H2O, that's in the small red box there, you need 1 mole of oxygen. To make 1 mole of water, you need 2 moles of hydrogen. When you have 1 mole of water, it's going to weigh 18.02 grams. If you have 1 mole of water, you're going to have 16 grams of oxygen. 1 mole of water, you're going to have 2.02 grams of hydrogen. If you have 1 mole of water, you have 6.022 times 10 to the 23rd water molecules. That's what 1 mole means. You're also going to have 6.022 times 10 to the 23rd oxygen atoms in 1 mole of water. And finally, in 1 mole of water, you're going to have 1.204 times 10 to the 24th atoms of hydrogen. So then the question is, what if we don't want exactly 1 mole? What if we want 2 moles? What if we want 4 moles? What if we want 6.72 moles? Then what do? Then you multiply any of those other numbers you see in that big red box by however many moles of water you want. So if you want 2 moles of H2O, for example, then you're going to need 2 moles of oxygen. That's going to equal 2 times 16 or 32 grams of oxygen. And that's going to be 2 times 6.022 times 10 to the 23rd atoms of oxygen. So you just multiply. It's like you have a recipe to bake a cake. We want to bake 1 cake. It takes a cup of sugar and 3 eggs. If you want to bake 2 cakes, you need 2 cups of sugar and 6 eggs. If you want to bake 3 cakes, you need 3 cups of sugar and 9 eggs. You just multiply all the ingredients by however many cakes you want. It's the same thing here. So let's get into some examples. How many grams is 3 moles of H2O? So look at that. Look in that box. You see that 1 mole of H2O is 18.02 grams. So there are 3 times 18.02 grams of water, which equals 54.06 grams of H2O in 3 moles of H2O. Now I want you to write your answers out exactly like this. I don't want you to just scribble down a number. I want you to see this relationship and see how it's calculated. I want you to reinforce it. It takes a little more writing, I understand, but I want you to be sure you see what this relationship is. Let's keep going. How many moles of hydrogen? And that's the way I want you to write this. It's a unit of measure, moles, and a substance, hydrogen in this case. So how many moles of hydrogen are needed to make 4 moles of H2O? So what you do is you look up at the in the moles column inside the big red box, and you look at the hydrogen row, and you see that there's 2 moles of hydrogen in 1 mole of H2O. So everything in that big red box is related to 1 mole of H2O of water. So it's asking how many moles of hydrogen are needed to make 4 moles of H2O. So if you want 4 moles of H2O, you need 4 times 2, or 8 moles of hydrogen. So there are 4 times 2 equals 8 moles of hydrogen are needed to make 4 moles of H2O. In other words, you need twice as many moles of hydrogen as moles of H2O. You need twice as many bicycle wheels as you want bicycles. If you want to make a bicycle, you need 2 wheels. If you want to make 100 bicycles, you need 200 wheels. If you want to make 1,000,000 bicycles, you need 2,000,000 wheels. Okay, so it's just that relationship, that 2 to 1. How many moles of oxygen are needed to make 3 moles of H2O? Now, I encourage you to pause the video, just think about it, just look at it. You don't have to write down answers here yet. So how many moles of oxygen are needed to make 3 moles of H2O? So if I want 3 in that little red box, in the small red box, then I have to multiply moles of oxygen by 3. So I look under the moles column and the oxygen row, and you see there's 1 mole of oxygen in 1 mole of water. So if I want 3 moles of water, I'm going to need 3 moles of oxygen. There's 3 times 1 equals 3 moles of oxygen are needed to make 3 moles of water. So you need 1 bicycle seat for each bicycle. So if you want to make 1 bicycle, you need 1 seat. If you want to make 100 bicycles, you need 100 seats. 1,000,000 bicycles, you need 1,000,000 seats. So if you want to make 1 water molecule, you need 1 oxygen. If you want to make 3 moles of water, you need 3 moles of oxygen. How many grams of oxygen are needed to make 3 moles of H2O? So now we're asking for grams. So you go over to the molar mass, that's the grams, molar mass column, and you look in the oxygen row, and you see that for 1 mole of water, you need 16 grams of oxygen. Right there, okay? So if you want 3 moles of water, you need 3 times 16 grams of oxygen. So there are 3 times 16, which equals 48 grams of oxygen in 3 moles of H2O. Again, it's just like I want to emphasize, just like a recipe for a cake. Okay, you have a recipe for 1 cake. If you want to make 2 cakes, you need twice as many of all the ingredients. If you want to make 100 cakes, you need 100 times as many of all the eggs and sugar and flour and all the ingredients. It's just called scaling. You're scaling up, okay? Okay, finally, how many grams of hydrogen are needed to make 7 moles of H2O? So if we look there, we see to make 1 mole of H2O, we need 2.02 grams of hydrogen. You look in the hydrogen row, H row, and in the molar mass grams column. And they intersect at 2.02 grams for hydrogen, grams of hydrogen. So if you want 7 times that many moles of water, you need 7 times 2.02. So there's 7 times 2.02 grams of hydrogen, which equals 14.14 grams of hydrogen, are needed to make 7 moles of H2O. Okay, let's finish up with some that deal with the number of atoms or molecules. How many molecules in 3 moles of H2O? Well, you can see in 1 mole of H2O you need a mole, 6.022 times 10 to the 23rd water molecules. So there are 3 times 6.022 times 10 to the 23rd molecules of H2O, which equals 1.807 times 10 to the 24th molecules of H2O in 3 moles of water. How many atoms of hydrogen are needed to make 4 moles of H2O? So in 1 mole, this one gets a little more complicated. In 1 mole of H2O, you need 2 moles of hydrogen atoms. That's 2 times 6.022 times 10 to the 23rd. So if you want to make 4 moles of H2O, you're going to need 4 times 2 times 6.022 times 10 to the 23rd. And that's going to be 4.818 times 10 to the 24th atoms of hydrogen are needed to make 4 moles of H2O. Again, pause if you need to and just think about that a little bit. Finally, last one, how many atoms of oxygen are needed to make 6 moles of H2O? So for 1 mole of H2O, you need 1 mole of oxygen, which is 6.022 times 10 to the 23rd atoms of oxygen. So if you want to make 6 times that many moles of water, you need 6 times 6.022 times 10 to the 23rd, and that's 3.613 times 10 to the 24th atoms of oxygen are needed to make 6 moles of H2O. So now let's look at some ways of writing molar mass that you're going to see practically every day in this class. So we now have found a way to relate moles to number of atoms or molecules or grams of the substance. So here's the molar mass for water. There it is. We computed that on an earlier slide. So 1 mole of water is 18.02 grams of water. So the way you write that as an equivalency, this is called an equivalency. The first one is 1 mole H2O equals 18.02 grams H2O. And I'm going to emphasize this way of writing where you write the unit of measure, moles or grams, and then the substance, in this case H2O. Because you're going to, in a problem, you're going to be dealing with moles and grams in different, you'll be dealing with moles and grams, but you're also going to be dealing with different substances, H2O, CO2, CH4. And so you've got to keep track of not just the unit of measure you're dealing with, but what's the substance. So there's 1 mole of H2O equals 18.02 grams of H2O. That's called an equivalency. Now there's a shorthand way to write that you're going to often see in a problem, and that is the molar mass of H2O is 18.02 grams per mole. So that's kind of a shorthand version of writing what you see up above in the equivalency. In other words, there's 18.02 grams of H2O for every 1 mole over 1 mole of H2O. So you don't see the 1 in front of the mole, you don't see the letters H2O after the grams and moles, but that's what it's saying there. Finally, the conversion factors are going to be critical to know how to get these from the equivalency, but it's very simple. Conversion factor, you simply take one side of the equivalency and put it over the other. So we take 18.02 grams of H2O and we put it over 1 mole of H2O. Now we go and we just reverse it, we flip it. We put 1 mole of H2O over 18.02 grams of H2O. Those are both true statements. You say, but one's flipped over and they don't look the same. It's 18.02 over 1 or 1 over 18.0. Those don't look like the same number, but they are. As long as you have units of measure attached to them, then you can do that. Let me give you an example. The way you would think of this. There's 12 inches in 1 foot. We all know that. So you can say there's 12 inches for every 1 foot. But it's also true to say there's 1 foot for every 12 inches. Those are both true statements. You just said them in a different order. It's the same thing here. You're saying the same thing, it's just in a different order, okay? You'll get used to this concept because you're going to practice it a lot. All right, and that takes care of this lesson. It was a long one. Some of the lessons will be longer. This is a super important lesson, so I want you to really focus on this and molar mass and how to compute those, and we'll do a lot of practicing of this, and you'll end up using this concept throughout the rest of this course almost every day.